Good evening, everyone. Welcome to another session of the Network Seminar Series hosted by the Center for Networked Intelligence at the Robert Bosch Center for Cyber-Physical Systems, IAC. Today's talk is by Dr. Siva Theja Maguluri, and he will be speaking on transform methods for queuing asymptotics. Dr. Siva Theja Maguluri is Fouts Family Early Career Professor and Assistant Professor in the H. Milton Stewart School of Industrial and Systems Engineering at Georgia Tech. He obtained his PhD and MS in ECE as well as MS in Applied Math from UIUC and BTech in Electrical Engineering from IIT Madras. His research interests span the areas of control, optimization, algorithms, and applied probability. In particular, he works on reinforcement learning theory, scheduling, resource allocation, and revenue optimization problems that arise in a variety of systems, including data centers, cloud computing, wireless networks, blockchains, ride-hailing systems, etc. His research and teaching are recognized through several awards, including the Best Publication in Applied Probability Award, NSF Career Award, Second Place Award at Inform's JFIG Best Paper Competition, Student Best Paper Award at IFIP Performance, CTL BP Junior Faculty Teaching Excellence Award, and Student Recognition of Excellence in Teaching, Class of 1934 CIOS Award. Before we move on to the talk, we would like to request the audience to subscribe to our Google group for information on future talks. You can also visit our website for more details. I will be pasting the links in the chat box. Please do check. Finally, we request the audience to keep your microphones on silent for the duration of the talk. And for questions, you may ask Dr. Siva Theja directly. Over to you, Dr. Siva Theja.
Thanks a lot for the generous introduction, Anshri, and thanks for inviting me to give this talk. This is designed to be a little bit of a tutorial style talk, so I'll get into some of the mathematical details. So it's best to interrupt me whenever you have a question to clarify, because it doesn't make much sense to wait till the end to get clarification about something at the very beginning. And I'll also make some pauses throughout the talk. Those are also good times to ask questions, but feel free to interrupt me. Today's talk is joint work with my former student Daniela, who is currently a faculty member at College of William and Mary, and my current student Prakirthraj Jinjwala. Stochastic processing networks arise in a variety of systems, including wireless networks, data centers, cloud computing, transportation systems, and so on. In pretty much all these systems, there are limited amount of resources, and then jobs of various types, whether they're packets to be transmitted or customers that need to reach their destination. These jobs arrive into the system, and they either get served by one server or a series of servers, and then eventually they depart. And the question is, how do you allocate resources, limited resources to these jobs in order to maximize the certain overall objective in the system? And typically the objectives one looks at are throughput and latency. And these kind of questions can be answered using tools from queuing theory. And the area of stochastic networks essentially studies these problems. So the performance metrics one looks at are primarily throughput and latency. So in terms of throughput, essentially the idea is that if you think of data center, so let's say Google has invested lots and lots of money to build a data center. Now they want to get the maximum possible bang for the buck. In other words, they want to use this data center to maximize the amount of throughput, maximize the amount of requests they can process. This is usually characterized by something called the capacity region. For a given system, one can define the capacity region. And the idea is that if the arrival rates are outside the capacity region, the system will be unstable. If it is inside, then it is possible to stabilize the system under some algorithm. And the goal is to find such algorithms. And usually analyzing throughput is relatively easier than analyzing delay. So in some sense, throughput is the first order metric and delay is the second order metric. So when one asks for delay, one is actually taking the user's point of view. So as a user, I don't care how much money Google has invested and whether they're getting good efficiency of their data center or not. All I care is how fast do I get my cat pictures. So a natural way of looking at this is in terms of mean delay to characterize what the mean delay experienced by users is. But a more refined metric is to look at the tails, 99th percentile. So usually many customers have SLA, service level agreements with service providers, and the service providers guarantee that the 99th percentile delay will be blocked. And getting a handle on these tails is also equivalent to getting handle on the moments and distribution of delay. And again, studying delay is in some sense is also equivalent to studying Q-length. So in this talk, I'm going to primarily focus on looking at mean and the distribution of Q-lengths. So in order to study resource allocation problems, like I mentioned earlier, one uses queuing models. And the issue with queues is that if you have a single server queue, pretty much any question you ask can be answered. Actually, even that is not entirely true, as we will see. And once you go beyond a single server queue, then pretty much any question that you ask is extremely hard to answer, especially to give closed form expressions for delay and things like that. So what one does is one looks at these systems in certain asymptotics. And the idea is, if you understand the system in the asymptotic regime, if you design the optimal algorithm in the asymptotic regime, hopefully it's going to work well in practice too. And there's several regimes that people look at: mean field regime, sometimes large deviation, and heavy traffic. So today we are going to look at heavy traffic regime. This is a picture of Midtown Atlanta, very close to Georgia Tech, and you can see heavy traffic. So in heavy traffic, the idea is you load the system very close to its limiting capacity, and then you see the performance. The delay usually blows up, but you see how it blows up, and you want to minimize the rate at which it blows up. So in this talk, I'm going to talk about transform methods for heavy traffic analysis. Like I mentioned earlier, this talk, instead of focusing on a particular results, it will focus on the method itself. So I'll kind of present three results to show how the method can be applied and to show its power. And at the very end, if time permits, I'll talk about a few more results. So there are several other methods that also are used in are also used to study heavy traffic limits, and I will not talk about those today. Diffusion limits, use of diffusion limits is the classical approach. So one of the messages I'm trying to convey in today's talk is that using transform methods is a lot easier than using diffusion limits, and consequently you can study more complex systems using transform methods. Stein's method is a very powerful approach that was developed recently. It has its pros and cons, but unfortunately we will not be talking about it today. Drift method is very closely related to transform method. In fact, transform method evolved out of drift method. We'll see that connection in today's talk. And finally, BAR approach is also very closely related to transform method. I'll not talk about it today. So this is the outline of the talk. I'll start with a single server queue, and then I'll state and prove the result on its heavy traffic behavior. This result was originally proved by Kingman almost 60 years ago using the diffusion limits approach. However, today I'm going to actually present the entire proof modulo some technical details using the transform method. This essentially shows how simple transform method is. Then I will very quickly talk about load balancing system, which was, again, the result here was proved 45 years ago. So again, I'll present how we obtained this result using transform method. And the main message here is to talk about something called state space collapse. I'll explain what it is as we go along. Then the third result I'm going to present today is actually new. It's not 45 or 60-year-old result anymore. In fact, it's actually brand new result. I think the archive paper will come out later today. So it's going to be on data center networks and input queue switches and the heavy traffic limiting distribution in input queue switches. The key challenge here is that the state space collapse is going to be multidimensional. I'll explain what that means. And essentially this result shows both the power of the method and what are the challenges in using the method. And finally, if time permits, I'll very briefly talk about some of the other results we were able to obtain using transform methods. So without any further delay, let's jump right in. So single server queue, I like to think about discrete time queuing models as opposed to classical continuous time models that you may have studied in a queuing course. So time is discrete. In each time, you have arrivals, and these arrivals happen in an IID manner. The number of arrivals in time slot k is a random variable a of k, that's IID. It has some mean lambda and variance sigma square, sigma a square. And the number of potential services in each time k is S of k. And that is also an IID sequence of random variables with mean mu and variance sigma s square. And QK denotes the number of customers in the queue currently. And one can show that this is actually equivalent to continuous time queuing model, the GG1 model, but we'll not worry about that connection. So the queue length evolves as follows. The queue length in the next time slot is the current queue length plus the new arrivals minus the potential departures. Except that, suppose my current queue length is 0 and I have 0 arrivals, and then my potential service S, it's just an IID random variable. It says that I can serve 3 customers right now, but there are no customers. So queue length cannot go negative. So I put this bracket plus to ensure that the thing inside does not go negative. So if the thing inside is negative, the bracket plus makes sure the whole thing is positive, is 0. If Q plus A minus S is positive, bracket plus doesn't do anything. So essentially, this bracket plus is projection onto the real positive real axis, and it's a nonlinear operation. So in some sense, one can think of all of queuing theory as a way to deal with this bracket plus, because if you didn't have it, it's all linear, and then one understands linear systems quite well. But this makes it nonlinear, and understanding this nonlinearity is at the heart of queuing theory. Sometimes it's called Skorohod map and so on. So being a very simple-minded fellow, I say that, oh, I don't like nonlinearity, so I'll make it look linear. So I'll introduce a new variable called unused service. What is this unused service? If Q plus A minus S is positive, this unused service is 0. If Q plus A minus S is negative, let's say it's minus 3, U takes value plus 3 so that the whole thing becomes 0. Now it looks linear, so I can do whatever I want. But just by redefining things, difficulties don't go away. The thing is, this U is strongly dependent on Q, A, and S. So dealing with this U is not easy. And essentially, we'll see how we'll handle U. So one thing to notice is that Q times U, QK plus 1 times UK is always 0. Why is this? Suppose UK is 0, then 0 multiplied by anything is 0. So obviously, the product is 0. Suppose UK is not 0. What is unused service? It was introduced to ensure the whole thing doesn't go negative. When is this non-zero? It is non-zero when this Q plus A minus S would have been negative, like minus 3. Then U takes a non-zero value to make the whole thing 0. So whenever U is non-zero, QK plus 1 is going to be 0. So the whole thing is always 0. So this is going to be like a defining quantity that we're going to exploit as we go. Okay, now from classical queuing theory, we know that if arrival rate is less than service rate, the system is stable. I'll not get into the definition of stability, but for those of you that know Markov chains, for me, stability means that the underlying Markov chain is positive recurrent. But the thing is, in GJ1 queue or my discrete time queue, one cannot obtain closed form formula for the queue lengths. So that's the reason we want to look at an asymptotic regime. So here we are looking at heavy traffic regime, lambda approaches mu. In other words, I define epsilon to be the heavy traffic parameter mu minus lambda. And I'm interested in the regime as epsilon goes to 0. So the main result is that the queue length actually blows up to infinity as 1 over epsilon. So I multiply by epsilon. So I look at epsilon times q, and I look at what happens to it in the limit. Q is a random variable, mind you. And in the limit, it converges in distribution to an exponential distribution with mean the average of both the variances. So this is in some sense the central result in heavy traffic theory of queues. One can think of this as being analogous to central limit theorem in probability theory, in the sense that in some asymptotic regime, you can say under appropriate scaling, that is multiplying by epsilon, you can give exact distribution of queue length, and it only depends on the first and second moments of the arrivals and service. It doesn't depend on their entire distribution. So I'm actually going to do the proof right now. But before I do the entire proof, first I want to show a simpler proof by Kingman, where he gets the mean, not the entire distribution, but only the mean. So essentially what Kingman does is he looks at the system in steady state. In steady state, based on the definition of steady state, if you take any expectation, it doesn't change over time. So the expectation of q square at time k plus 1 is same as q square at time k. Now I can substitute for qk plus 1 using this formula, and then expand it using binomial theorem, and then rearrange the terms. Then I get something like this. Now this mu minus lambda here is epsilon. So like I told you, the queue length is kind of blowing up to infinity as 1 over epsilon. The second term here, one can show quite easily that this is a constant. The first term is going to infinity as epsilon goes to 0. Second term is constant. So the second term is negligible. Now I can multiply by epsilon on both sides, take the limit. then the second term vanishes. I'll just have the first term. This is the second moment. One can show that the second moment here in the limit is same as the variances. The mean essentially goes to 0. So what we got is we showed the heavy traffic limiting value of the Q length to be equal to this value, but we want the entire distribution. So Kingman actually wrote several papers in 1962. In one of the papers, he proved this result. In a different paper, he used diffusion limit approach to get the entire distribution. However, in 2013, Abandonments and Srikanth came up with a different method. They extended this drift method to get the entire distribution. And this is what they did. You start with Q square as the test function, set its drift to 0, like we did in the last slide. Then you'll get the expected Q length, and this is the answer. Then Srikanth and Ariel Matz essentially took Q cube as the Lyapunov function, test function, set its drift to 0. Then they get expectation of epsilon square Q square, and it looks like this. And then they kept doing this using Q power m plus 1 as Lyapunov function. You can get the mth moment. And then in order to do this, one uses induction and uses all the previous Q length bounds. Now, once you get all of these results, one can ask, is there a single distribution that has all these moments? And the answer is yes, that's exponential. So essentially, one has shown that epsilon times Q converges in distribution to the exponential. This is called method of moments. Now, one has to repeat this process inductively many, many times, and then one has to use all the previous moment bounds to get the next moment bound. So, but if I look at all this test function and then I simply add them after multiplying by appropriate constants, then what I have is Taylor series of exponential. And similarly, here I get expectation of e power epsilon q. So a natural idea that this leads to is, what if I use exponential as a test function? And this essentially leads to transform method that was initially proposed by Daniela and me in 2019. So now what I do is, instead of, now I want to get the limiting distribution in one shot without going through the induction. So I take exponential test function, set its drift to 0. And so earlier when I used quadratic test function, I substituted for qk plus 1 and expanded in binomial theorem. But there is no binomial theorem for exponential powers. So what do I do? So I think this, so I'm stuck in the very first step. So this is where we stumbled upon this beautiful lemma. It says that you can ignore theta for the time being. Theta is just a variable. We'll see its role later. So it says that e power epsilon qk plus 1 minus 1 times e power minus epsilon uk minus 1 equal to 0. Question for the audience: why is this lemma true? I told you this is a tutorial, so there's going to be a quiz. This is the quiz time.
Is it because qk plus 1 uk equal to 0?
That's correct. Qk plus 1 times uk equal to 0. That's the reason. So let's actually unwrap this. So if you look at the function I have here, I have e power x minus 1. The first thing to notice is that e power x minus 1 is equal to 0 if and only if x equal to 0. So now, suppose u equal to 0, this guy, this e power u minus 1 equal to 0. So the product is 0. Very good. Suppose u is not equal to 0, then we know that qk plus 1 is 0, which means this guy, the first term will be 0, so the product is always 0. So when we first came up with this lemma, Daniela had to do like pages and pages of calculations to come up with this lemma, and once she found it, we saw that the proof was just one line. There is nothing to prove. Anyway, so once we have this lemma, then I substitute, then I expand this, I multiply this. So I put a minus here. There's a reason for that, because when you multiply this, you'll get qk plus 1 minus uk, and that becomes q plus a minus s. So I expand this, I'll get 4 terms. I write them like this and set expectation on both sides. And now setting this drift equal to 0 is same as simply dropping this plus 1. So I replace this qk plus 1 by qk. So essentially what I have is I have this equation. I just rewrote the equation from previous slide. I did not put the plus 1 here. Now this a and s are independent of everything else in the system. So this is product of exponentials. Because of independence, I can write it as product of expectations. So, and then after rearranging, I'll get something like this. Now I'm pretty much done. All I want is to find the limit of this guy. So I take limit of this as epsilon goes to 0. But the only problem is if I put epsilon equal to 0, I'll get 0 by 0 form. So once I have 0 by 0 form, we use standard tools from calculus. In particular, we use Scalar Approximation. We expand both the numerator and denominator in Taylor series, and then we'll get a bunch of terms. One can show that this particular term is epsilon. So after simplifying and substituting the values for all these expectations, we'll get something like this. Cancel theta epsilon square, take the limit, higher order terms don't matter, and then we'll get this. Essentially, there's nothing much here. It's Taylor series, and then doing the algebra carefully. Then this formula almost pops out. I didn't have to do anything to make this formula appear. It just shows up. And this turns out to be the MGF of exponential random variable with mean sigma square over 2. So, and on the left-hand side, what we have is the reason I put this theta is because now this looks like an MGF of epsilon q. So in the limit, so essentially I showed you that the MGFs converge to MGF of exponential random variable. And this implies that I have convergence in distribution. So this completes the proof of the theorem about heavy traffic behavior of in a single server queue. Any questions? Okay, so essentially transform technique at a very high level is a two-step procedure. The first step, I did not talk about it so far. It essentially involves showing that the Markov chain is positive recurrent so that the steady state distribution exists and the appropriate mean is finite so that you can set the drift to 0 in steady state. If steady state does not exist, that's meaningless. So once you know steady state exists, then you take the exponential test function and set its drift to 0. Now, there are many kinds of exponential functions we can use. I basically showed something of this form where theta is a real number. And this is essentially moment generating function of a random variable. And this is also same as two-sided Laplace transform. And to set the drift of this guy to 0, I should first show that this expectation, this MGF exists. If it does not exist, I am essentially doing infinity equal to infinity. And if I start with infinity equal to infinity, I can get any nonsense out of it. So I should first show that this is finite so that my first step in the proof is some finite quantity equal to a finite quantity. Then what I get is meaningful. So this involves an additional step showing that the MGF exists. A second approach is instead of using theta, I can use j omega. J is square root of -1. Omega is a real number. So I can pick numbers on the imaginary axis. And now instead of working with two-sided Laplace transform, I'm using Fourier transform. And this is called the characteristic function of random variable. And the advantage with this is this always exists because the absolute value of this guy being a complex exponential, it's always 1. So you don't have to worry about existence. The only issue is you have to deal with complex numbers. But the good thing is there is also a lot of theory from complex numbers that you can exploit in certain settings. And the third approach is that my Q length is always positive. So I can work with only thetas that are negative. Then this guy always exists because if theta is negative, e power theta q is less than 1. Then I don't have to worry about showing existence. And this is called the one-sided Laplace transform. And this approach is used in the BAR approach that I mentioned earlier. So in the various results that we use, we actually mix and match. In different problems, we work with a different thing. For a single server queue, you can use any of the three. But in other problems, one approach turns out to be easier than the others. So the key takeaways so far are that to get heavy traffic bounds or bounds in general, you should work with steady state and set the drift of a function to 0. You can work with either quadratic or polynomial test functions. That's called the drift method. Or if you work with exponential function, we call it transform techniques. And the key message is that the unused service is important. And finally, transform method greatly simplifies the proof. Essentially, I showed all the key steps of the proof on a single slide. Whereas if you use the classical diffusion limit approach, it would take several pages. So any questions? This is a natural point to pause.
So I have a couple of questions, but I was thinking maybe I'll ask them in the end.
Okay.
Thanks.
Okay, cool. So looks like I'm going way slower than I initially thought. So I guess I'm going to skip the load balancing part. I'll explain and then I'll jump right into the third part on input queued switch. So essentially, the only thing I wanted to tell about load balancing is that it satisfies something called complete resource pooling. And under complete resource pooling, the system behaves. You have many queues in load balancing system, but in the heavy traffic limit, they all behave as if they're single server queue. Therefore, in the limit, the answer is exponential, very similar to single server queue. But there are many systems that satisfy this complete resource pooling condition, and they're well studied in the literature. But there are also many other systems that do not satisfy complete resource pooling, which means they don't they don't behave like a single server queue. In particular, they don't satisfy something called state space collapse. They do have state space collapse, but it is not onto a line. When state space collapse happens to onto a line, the system behaves like a single server queue. But when it happens to a bigger subspace, multidimensional subspace, it doesn't behave like a single server queue. And that's what we see in an input queued switch. An input queued switch is motivated by data centers. So in cloud computing is powered by data centers where you have lots and lots of servers. The servers store data of various forms, and there's a network that connects these servers to facilitate exchange of data. So this network is designing this network is an active research area. There's certain topologies people use, certain hierarchical topologies, but the goal in design of these networks is that is for this network to be approximately behave like a huge switch. You can go to a store and then buy, I don't know, 16 cross 16 switches, or you can go to Cisco and ask them to make you a 500 cross 500 switches. But now I want 100,000 cross 100,000 switches. Those don't exist. So people buy 500 or 1,000 cross 1,000 switches and then connect them in order to get a network that's logically equivalent to a huge switch. Now, what do I mean by a switch? So here is an abstract model of a switch. You can think of it as a matrix of queues. There are n inputs and n outputs in a switch. So my inputs correspond to the rows and outputs correspond to the columns. So there are n square queues in all. So this queue corresponds to jobs that arrive at input I that have to go to output j. Now packets arrive to each of these queues independently across time, across space, IID. Sorry, they're IID across time, across space, they're independent, but they need not be identically distributed. And each packet needs exactly one time slot of service. But the key constraint is that at each time, only some queues can be active. What queues can be active? In each row, at most one queue can be active, and in each column, at most one queue can be active. So the blue set of queues can be active at one time. In other words, the set of active queues must form a permutation matrix. Now the question is, which set of queues should be served in each time slot in order to maximize throughput and minimize delay? This is the scheduling problem in a switch. And the goal is to design a scheduling algorithm that has low complexity, because every time you have to calculate the schedule. And it should lead to small delays, both mean and the tails. And hopefully this delay does not grow with the size of the network, given today's data centers. And turns out all of this is achievable. And that's basically the result I'm going to present today. So firstly, let me present the algorithm that we use. It's called the max weight algorithm. So remember, the problem is at each time, in each time slot, discrete time system, in each time slot, I have to figure out which set of queues are active. So, and which permutation, and the set of queues that are active should always correspond to a permutation. So all I do is list all possible permutations, calculate the weight of each permutation. What is the weight of the permutation? Look at the queues that are active in that permutation, just add up their weights. So in the first permutation, I have all these diagonal queues, 5 plus 1 plus 2 is 8. So its weight is 8. So I calculate this for all permutations. Now pick the permutation with the maximum weight and schedule those queues. So I'll schedule this guy, this guy, this guy, and one packet from each of those queues will depart in each time. So this is called the max weight scheduling algorithm. The max weight algorithm is well studied in CS literatures, and it can be implemented with computational complexity of n power 2.5. So that's good. So it has fairly low complexity. Now the question is, what is its queuing behavior? Does it maximize throughput, and does it minimize delay? So let's talk about throughput. So to talk about throughput, we should look at arrival rates of all the queues. There are n square queues, so there are n square arrival rates. So I'll call them lambda ij, and I'll think of them as a matrix. Now, one can show that a condition that's required for stability is that the total arrival rate in each row must be less than 1. Total arrival rate in each column must be less than 1. Why? In each time slot, in each row, I'm scheduling only one queue, and I'm serving only one packet from that queue. Which means at each time, at most, I can serve one packet from each row, one from each column. And which means if I'm outside these conditions, it'll be unstable. That's straightforward. Now the question is, suppose my lambda satisfy these conditions, will it be stable? Suppose the total arrival rate for each row and column is strictly less than 1, will it be stable? So essentially, I'm using this picture to denote these arrival rates. This is obviously a cartoon because I have this picture should be drawn in n square dimensional dimensions. And unfortunately, the version of PowerPoint I'm using only supports 2 dimensions. I can't draw n square dimensions. So we'll just do with this picture. So it was shown back in the 90s that if you use max weight algorithm, throughput is maximized, which means if you give me arrival rate vector anywhere in this capacity region, the system will become stable. Firstly, it's not clear a priori if there is a single algorithm that makes the system stable for any arrival rate in the capacity region. Turns out such algorithms exist. They're said to be throughput optimal, and max weight is one of them. Now, I want to understand the delay behavior. And based on our experience from single server queue, we shouldn't expect to be able to say much about delay in general. So again, we'll look at heavy traffic regime. We'll approach the boundary of this region, which means we'll make all these constraints tight. In other words, I'll make the total arrival rate in each row and column that should be less than 1. I'll make it equal to 1 minus epsilon. Total arrival rate for each row and column is 1 minus epsilon. Moreover, I'll assume that the traffic is uniform. The rates are same across all queues, in which case the rates should be 1 minus epsilon over n. So this is my assumption. Some of the results I present are true without uniform traffic, but for some of the results we need uniform traffic assumption. And then let me also assume that the variance of all the arrival streams is the same number sigma square. The first result we have, which was proved 6 years ago with my advisor Shrikant, is that in the heavy traffic limit, the queue lengths multiplied by epsilon. I have n square queues. I add all of them up. Then we found an exact expression for the mean queue length. It looks something like this in this setting: n times n minus half times sigma square. And one can show that this immediately implies that the delay does not scale with the size of the data centers. We can use Little's law and so on. I'll not go into the details of that. Then a natural question is, can we find the distribution? And now I have not a single queue, n square queues. So I want to find the joint distribution of all those guys in the heavy traffic limit. And actually finding the mean and the distribution has been a long-standing open problem in stochastic networks. In 2016, we answered the mean question. And since then, I've been obsessed about the distribution question. And we essentially developed transform method in my group over the last several years to handle the distribution question. And finally, Prakrit kind of has an answer for the distribution, and that's the result I'm going to present today. This is the result that is brand new. It's not even public yet. The archive paper will be out today. The result was almost done like last fall. We sent it to a conference, but we never made the result public. So firstly, I should say that we haven't quite completely proved the result. We have one hole in the proof, and we stated it as a conjecture. I'll state the conjecture later. Let's first focus on the result, and we'll worry about the conjecture later. So I have n square queues. Look at any of them. Then if I multiply by epsilon and take the limit, it has the following distribution. So firstly, I take 2n gammas. In reality, this is a Greek letter epsilon. It sounds so weird. I'll just call it gamma for the time being. It looks like gamma anyway. So I take 2n IID exponential random variables. I'll denote them by gamma and gamma hat, n gammas and n gamma hats, exponentials with mean sigma square over 2. And I'll take the minimum of them to be gamma min. So gamma min is also a random variable. For each realization of all these gammas, look at the minimum, that is gamma min. And the distribution of each of these q's is gamma I plus gamma hat j minus 2 gamma min. Let's actually parse this. There's a lot going on here. One way of thinking about it visually is as follows. My queue length is a matrix. It's an n by n matrix, n square queues. What I'm saying is that in the limit, it converges to a joint distribution that looks as follows. I have n rows and n columns. For each row, think of a random variable, which is gamma I minus gamma min. For each column, think of a random variable, which is gamma hat j minus gamma min. Now, the ijth entry is basically the row random variable plus the column random variable. And this is true for all the entries. Okay, let's take a step back. There's a lot going on here. So I have n square queues, and I'm interested in the joint distribution. A dumb question would be, are all these n square queues independent? And turns out they're not independent. This is not surprising because the max weight is kind of strong, introducing strong dependency between them. Then a second question is, are all the queues equal? This actually happens in load balancing. In load balancing, all the queues become equal. Are all these n square queues going to be exactly equal? This is saying no, not quite. They're not independent, they're not equal. These are two extremes. So this is saying they're somewhere in between. They have this row column structure. These rows have some number, columns have some number. These numbers are random. And then each entry is the row plus column. Then the next question is, are these row weights and the column weights independent? And the answer is not quite. If I did not have this pesky gamma mins over here, then I would have these gammas and gamma hats, and they're all independent, and the row and column weights would have been independent. Because of this gamma min, this row column weights actually become dependent, but it is like a very structured dependence. And the structure is also very interesting. So my gammas are all exponential, so they're positive, but I'm subtracting something. And when I subtract, it could possibly go negative, right? But turns out that I'm subtracting the minimum of all these guys, which means so all these entries are non-negative. And in particular, one of them is going to be exactly 0. So among all these 2n weights, the row weights and column weights, one of them is exactly 0. Everybody else is non-negative. So let's actually take a closer look. So what I'm saying is this Q length vector, it lives in n square dimensional space. It's non-negative, so it lives in the positive orthant in n square dimensional space. The question is, in the limit, can it take any value in the orthant? And the answer is no. Whatever value it takes in the limit, in the heavy traffic limit, it should have this structure. There are these row weights, there are column weights, and then each entry is the row entry, a row weight plus column weight. These n square queues are determined by these 2n numbers. So it's as if it lives in a lower dimensional space. What is the dimensionality of the space? There are 2n numbers, so a naive answer would be it's a 2n dimensional space. But actually, these numbers are not unique. This representation is not unique. If you give me w's and w tildes, I can subtract 1 from all the w's and add 1 to all w tildes. I'll get the same Q length vector. So I have some degree of freedom. And because of this degree of freedom, the actual dimensionality turns out to be 2n minus 1 and not 2n. And all these weights should be positive, which means to make it unique, I can decrease all these weights so that one of them is exactly 0. Then I have 2n minus 1 non-zero values. And this also shows why the dimensionality is 2n minus 1. Then the natural question is, where is this 2n minus 1 coming? Why is it important? And once you recognize why this 2n minus 1 shows up, then essentially the theorem is saying that all these 2n minus 1 weights are determined by these 2n IID exponentials. And in order to make one of them 0, subtract the minimum guy from all these weights. So this is the structure. Oh, by the way, in the previous slide, I talked about the distribution as well as the mean. So as a sanity check, you can calculate the mean of this, and then add up over all the n square q's, and indeed you'll get this. Very good. So let's understand why the Q length should live in this lower dimensional space. So remember, we are assuming that all the rows and columns, the total arrival rate is exactly 1 minus epsilon. So these are those equations. Another way of writing those equations is by using inner product notation. Lambda is my n square dimensional vector. It's a matrix, but I think of it as a vector for inner product purposes. Then EI is a matrix or a vector, which is simply one in the ith row, everything else is 0. Now, if I take dot product between the lambda vector, lambda matrix and this matrix, then essentially I get the row sum of the ith row. And I'm saying that is equal to 1 minus epsilon. So in the limit, that will be equal to 1. So I have n of these row matrices, n of these column matrices. And essentially what I'm saying is I take my lambda vector, take inner product with each of these guys, 2n inner products. All these inner products in the limit should be equal to 1. So that's a constraint I'm imposing in the limit on my arrival rate vector. And this ensures that it's on the boundary of the capacity region. So in other words, this arrival rate matrix in the heavy traffic limit lies at the intersection of 2n hyperplanes, and the normal vectors of these hyperplanes are all these e's and e tildes. So it turns out that when this happens, the corresponding Q length vector collapses to a cone spanned by all these 2n vectors. So if you want to think about it pictorially, again, this picture is not accurate. It's just a cartoon to explain the intuition. In reality, the structure doesn't quite look like this. It has a different structure in n square dimensions. So I have 2n, so I have these faces. Faces are hyperplanes. And I look at the intersection of these faces. So in reality, in my case, I have two end faces and I'm looking at the intersection of these two end faces. And I look at the normal vector and my arrival vector lies somewhere on this intersection. I look at the normal vectors of all these faces, and that gives a cone, and my Q length lives in this cone. And any vector in this cone can be represented as a conic combination of all these guys. Conic combination just means that it looks like linear combination, except that these weights should be non-negative. And that's exactly what we had before. And this is called multi-dimensional collapse because now my Q length doesn't live in n squared dimensions. It lives in a 2n minus 1 dimensional cone, but it doesn't live on a line. So there is state space collapse. It's in multiple dimensions. This is also said to not satisfy complete resource pooling condition. And so being in this conic combination, essentially it's same as having this kind of structure. Then the question still remains, why is it that it should collapse to this cone? It turns out that whenever you do max weight, not just in switch, take any algorithm, max weight is quite powerful. You can use it in many, many different resource allocation problems. Whenever you approach a point at the intersection of boundaries, max weight will have this kind of collapse. We proved it in a different result. But if you restrict to switch, if we take a step back, I was saying that you have this IID arrivals into all these queues, and in each time you take the maximum permutation and then schedule that. By scheduling that, you're serving those queues, you're draining those queues, you're decreasing those queues. You take the permutation of the maximum weight and you're decreasing the queues in that permutation. Then it is natural to expect that in the limit, all the permutations will become equal because I take the big guy and then decrease that guy. And if I ask you, what are the Q lengths under which all the permutations have exactly the same weight, it turns out that all the Q lengths in this cone and only the Q lengths in this cone satisfy that property. So this is an intuitive reason for why one should expect collapse into this region. Okay, so this state space collapse result we have proved. I'm not getting into the math here. I am just presenting the intuition. But this was proved in the 2016 paper with Srikanth. And then this was used to obtain the mean result in 2016. And now with Prakrit, we are trying to use transform method to get the joint distribution. And based on our intuition, based on what we saw in a single server queue, in transform method, we should take, so maybe I should stop, pause for a while. Are there any questions? I told you a lot in the last 10-15 minutes. Any questions so far on the switch? Okay, I'll take it as a no, and I'll move forward. So in order to get the joint distribution, based on what we learned about transform method in a single server queue, I need to set an exponential test function. Now Q length is a vector. So the corresponding MGF, essentially theta will be a vector. So theta is also an n squared dimensional vector. So I do something like this. I already showed state space collapse. So I know that Q length actually lives in a 2n minus 1 dimensional subspace. So I can restrict theta also to be in that subspace. And here we actually take theta to be complex numbers. I showed you 3 cases, theta being positive real, any real number, negative real, or imaginary number. Here I'm just combining everything. Theta is a complex number that lives in that cone. And after simplifying, doing some algebra, Taylor series, blah, 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 and most importantly, exploiting state space collapse in this process, we expect to get a closed form answer for the MGF of this joint distribution. That's what happened in a single server queue. I said this drift, and then I used the QU equation, and I did a bunch of math, Taylor series, blah, 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 and then a MGF popped up. But here, if I do that, unfortunately, an MGF does not pop up. Instead, I get an equation, weird equation that looks like this. So there are a bunch of things in this equation. You don't have to understand everything about the equation. There's some theta. Theta is just this variable. Because I'm thinking about MGF, I need a variable in the exponent. That is my theta. And n and sigma square we recognize. The new things are this L and M. What is L? L is indeed the limiting MGF. L is what we're trying to solve. This is what I want to find the closed form expression for. If I did not have M here, if I had some known expressions, then I could just send this on to the other side and done. I have a closed form expression. Unfortunately, I have this M here, and this M depends on this e power theta epsilon q as well as my unused service vector. So this has some complex dependence. One way of thinking about it is that, remember my probability mass in the limit only lives in this cone. this L corresponds to the entire joint distribution, especially the distribution in the interior, because if you look at any line, it has probability mass 0. And this M corresponds to the probability behavior on the boundary in a lower dimensional space, boundary of the cone. Okay, fine. So I have weird equation. Now what do I do with this equation? Can I solve it? Does it have a solution? Is it unique? If I show that it has a solution and it is unique and it corresponds to the joint distribution I showed you before, I'll be done. The proof would be complete. So the first thing we show is that indeed it has a solution. Take the joint distribution I showed you earlier and calculate the L and M for the distribution and plug it in. It verifies this. So at least this equation is not meaningless. It has a solution. Now there could be multiple solutions. We guessed the solution, plugged it in, it works. Now, maybe there are other solutions that we have not thought of. So at this point, we do not know if there are multiple solutions or not, but we strongly believe that it has a unique solution and it is the one that we already discussed. So if indeed this has a unique solution, that completes the proof. And that is our conjecture. The conjecture is there is a unique joint distribution on the cone that satisfies this equation. At this point, we don't know how to prove this conjecture, but we should be working in 2n-1 dimensional space. But if you look at special cases where the collapse is into a 2-dimensional space, then there is some literature, prior literature, which shows that equations of this form have a unique solution. And this was done by solving something called the Kalman's boundary value problem. This is a boundary value problem in complex domain. And that's the reason we use theta to be a complex number. But proving this uniqueness more generally is open. And until that is proved, our theorem statement will not be complete. That's why we had the uniqueness conjecture in my theorem statement. Okay, good. So key takeaways from this part is that transform method works when complete resource pooling is not true, when the collapse is onto a multi-dimensional subspace. And this is the first result of this kind. So, excuse me. So when complete resource pooling condition is not satisfied, there are very, very few results in the literature. And one of the reasons why switch was such an important problem in stochastic networks is it's kind of like a poster child for systems that do not satisfy complete resource pooling, that have this multi-dimensional collapse, that do not behave like a single server queue. In other words, that do not have a single bottleneck. Complete resource pooling means that in the heavy traffic, there's a single bottleneck. No complete resource pooling means there are multiple bottlenecks. So even though this illustrates the power of transform method, so this is the first result of this kind, but solving this implicit equation in general is challenging. So we need more tools to solve these equations, and that leads to many, many future directions that are still open. So I want to briefly summarize the results that we saw so far. We looked at a single server queue. We saw that epsilon q converges in distribution to an exponential in heavy traffic limit. I wanted to talk about load balancing system under join the shortest queue routing. We didn't quite talk about it, but it satisfies something called complete resource pooling. And what that means is there's a single bottleneck. The system, the state collapses to a line and it behaves like a single server queue, which means the queue length vector converges in distribution to all one's vector multiplied by an exponential. All the queues actually become equal, and each of those queues has this exponential distribution. I skipped this part. Then we talked about input queue switch, where complete resource pooling is not true. There's no single bottleneck. There are actually 2n bottlenecks corresponding to the row constraints and the column constraints. And we looked at max weight in a switch, and we have collapse into this 2n-1 dimensional cone that I talked about. And then the limiting join distribution has this matrix structure that we discussed in detail. And there is the open problem about showing the uniqueness conjecture. So I will pause here, and then I'll take the next 5 to 7 minutes to briefly talk about other places where we have used transform methods so far. Any questions at this point?
Maybe you can finish this and then we'll come back and take questions.
Okay, sounds good.
Thanks.
So one thing, this is ongoing work. We plan to complete the paper within the next month or so, also with Prakrit Jhunjhunwala, is to study queues with abandonment. We look at a single server queue, exactly same setup as before so far. Now these customers are impatient. So in each time slot, each customer tosses a Bernoulli IID coin with mean gamma. And then if it is a head, he leaves. He abandons the system. So first thing to notice is that now lambda need not be less than mu. Lambda can be a million. The Q is still stable. It doesn't blow up to infinity because abandonment will stabilize the system. Now, so I want to look at this system in heavy traffic. So again, I look at epsilon equal to lambda minus mu. Now epsilon can be both negative and positive. Lambda greater than mu is meaningless in a classical queue, but because of abandonment, lambda can be greater than q, epsilon can be positive. And the correct scaling we should be looking at, it turns out, is square root gamma times q. So actually in the heavy traffic here, earlier in heavy traffic, epsilon went to 0. The correct heavy traffic for this problem turns out to be when both epsilon and gamma go to 0, and the relative speed at which they go to 0 makes a difference. So this vertical line here shows 0 for epsilon. So now this leads to many regimes depending on the relative speed of epsilon and gamma. The first thing is when epsilon is like minus square root of gamma, epsilon is negative, so it's like minus square root of gamma. There could be some little of square root of gamma terms, we don't care. So when epsilon is like minus square root of gamma, essentially the limiting distribution is like a Gaussian, but it's truncated. You have to push it to the left. The mean of this is at minus c, and then take the positive part, q length can only be positive, take only this part and then renormalize it. This is the limiting distribution. And if c becomes 0, then this Gaussian essentially moves, and then the limiting distribution is like half of a Gaussian. Again, renormalized appropriately. And if epsilon is positive, c times square root of gamma, then this Gaussian moves further in, and again you have to renormalize, and this happens to be the limiting distribution. So this is very interesting. In classical single server queue, you had a single exponential. Now you have all these regimes, and depending on which regime you have, you get a different answer. Now, what if epsilon is very large? It's larger than the square root of gamma. I don't know, gamma power quarter or something like that. Then it turns out square root gamma times q goes to infinity. And whenever you are looking at an asymptotic regime and then your answer is infinity or 0, that means you're not looking at the right scale. So it turns out the right thing to look at here is you should subtract the mu. Basically, you have to center it appropriately. Then when you subtract the mu, you'll again get a Gaussian. So the behavior is essentially like this thing, except that there is no truncation anymore. This has come to the positive side completely. The Gaussian has moved to the positive side completely. That's why you had to subtract the mu. And finally, if we do this gamma power quarter kind of scaling, then I could do that in the negative side as well. Now epsilon is minus gamma power quarter. There's nothing sacred about quarter. It's all about the exponent being less than half. That's what is important. In this case, the q length becomes 0. The limiting square root gamma times q becomes 0. Again, if something is 0, that means the scaling is not correct. The correct scaling turns out to be whatever this expression is. If this is gamma power quarter, the q length is of the order 1 over gamma power quarter. So when you multiply with that, you'll get an exponential similar to the classical heavy traffic result that we saw. So this is one set of result. This is upcoming in the next month or two. A different kind of result. So I want to show in this slide and the next, I want to convey that transform methods are useful even beyond queuing theory. So in queuing theory, you have a server that is staying put. It's the server's job to stay there and serve customers. It doesn't go anywhere. It doesn't idle. And customers come, they get served, and they leave. But many recent applications such as ride hailing introduce something called matching queues. There are no servers that stay put. Servers also have arrivals, exactly like customers. Customers have arrivals according to some IID process. Customers are on the right side. Customers have arrivals according to IID process. Servers also have arrivals according to some IID process. And in each time, a server and a customer are matched. And once they are matched, they disappear from the system. Now, both the arrival rates should be equal. Otherwise, one of the queues would go to infinity. That is easy to see. But even if both the arrival rates are equal, the system is not stable. It is actually not positive recurrent. It's something called null recurrent. And the stability is usually defined as positive recurrence. So this is because if you have a symmetric walk on a line, it is null recurrent and not positive recurrent. So then the question is, how do I make this positive recurrent? How do I make this stable? So in order to make this stable, you need to have some external control. One control that people use is pricing control. That's why you have surge pricing in Uber. The idea is if there are lots and lots of drivers, then you reduce the prices so that the driver arrival rate decreases and the customer arrival rate increases. Then the system is moving towards stability. Then the queue length of drivers will drain. Similarly, if the lot of customers, you jack up the prices so that the arrival rate of customers decreases and the arrival rate of drivers increases, so these customers will be served. So what this means is, unlike a single server queue, this already, even in terms of stability, there is a lot richer behavior. Lambda is not less than mu. There is no simple condition like that. Instead, you need to have this control. Now we study this kind of system in heavy traffic. And what does heavy traffic mean here? It means that the control is going to zero. Then the system moves to the verge of instability, and that corresponds to heavy traffic. And how do I make the control go to zero? Here is an example of a control. Here is one kind of surge pricing. Essentially, what I do is, if the driver queue is above tau, then I jack down the prices by epsilon. And if the customer queue is above tau, then I jack up the prices by epsilon. In other words, if this queue is above tau, I decrease the arrival rate of this by epsilon. If this queue is above tau, I decrease the arrival rate of this by epsilon. Now, to make the control go to zero, I can do it two ways. One is epsilon becomes zero. If epsilon becomes zero, the control is going to zero. This is heavy traffic. The second way is I fix epsilon. I make tau go to infinity. I apply the control at larger and larger thresholds. And if tau goes to infinity, it's as if there is no control. The two ways I can the two parameters for me to control, to tune the control. And this epsilon goes to zero in the limit, tau goes to infinity. Now, there are many ways this can happen. One of those can be fixed, the other can go to the asymptote, or both of them can go to zero and tau respectively. And turns out the limiting behavior this time depends on the product of epsilon times tau. Epsilon goes to zero, tau goes to infinity, or both. And the product can either go to zero, or it can go to infinity, or it can go to a number between zero and infinity. And depending on these cases, the limiting distribution, now you have queues on both sides. So it's not just positive. The support of the distribution is on both sides. This basically plots the imbalance. The imbalance is Q2 minus Q1. So in this regime, we have Laplace distribution. Laplace essentially is two-sided exponential, because you're two-sided. This is analogous to classical heavy traffic in single server queue. There, since it was one-sided, you had exponential. Here it is two-sided. So you have two-sided exponential, which is Laplace. In the other extreme, you get uniform centered around zero. And in the between regime, you get hybrid, which is basically a hybrid of these two things. And this is joint work with my student, Sushil. The conference version was published last year, and we are in the process of submitting the journal version. The third result I want to show has no queue, no two-sided queue. It has nothing to do with queuing theory. This is about stochastic approximation more generally. To keep it concrete, think of stochastic gradient descent. A recursive algorithm that looks like this: xk plus 1 equal to xk plus step size minus gradient plus noise. I hope many of you have seen stochastic gradient descent. This is central to pretty much all machine learning algorithms. And the result I'm going to talk about also applies to stochastic approximation of contractive operators, reinforcement learning algorithms, and so on. But let's focus on SGD for concreteness. So in SGD, the step size plays a very important role. If the step size is diminishing according to some rate like 1 over k or something like that, one can show that SGD converges to the minimum of the function, assuming it's convex, smooth, strongly convex, whatever assumptions we need. But in reality, people like to use constant step size. Why? Because if you use constant step size, SGD initially makes very fast progress, geometrically fast. But the problem is it doesn't converge. After some point, it just wanders around x star. It doesn't converge to x star. But initially it makes very good progress, and that's why practitioners love constant step size SGD. Now the question is, can you say anything about its steady state behavior? So firstly, one can show that under constant step size SGD, as time goes to infinity, it has a stationary distribution. That's why it kind of wanders around x star. The stationary distribution is not a delta around x star. That would mean that you have convergence. It has some non-trivial variance. Now the question is, what is the stationary distribution? Turns out there is no way to give a closed form expression. This is analogous to saying that for a GG1 queue or a single server queue, there's no formula, analytical formula for the steady state distribution. This is also a steady state distribution. There's no analytical formula. Then the question is, can we at least look at some asymptotic regime? In queues, we looked at the regime when epsilon, the heavy traffic parameter, goes to zero. Here, we look at the regime when alpha, the step size, goes to zero. it turns out that again, we have to come up with the right scaling. What we showed is that if you take this Q length distribution, this is supposed to be X alpha infinity. This is wrong. Infinity shows that it's steady state distribution, and there is an alpha here, which means for step size alpha. Now, when I divide it by square root of alpha and take the limit, what I get is Gaussian. And we proved this for SGD of smooth strongly convex functions, linear stochastic approximation, and contractive stochastic approximation. But if you go beyond these three assumptions, it turns out that the scaling is not square root of alpha and the limiting distribution is not Gaussian. More generally, we expect Gibbs, but that's not proof. That's future work. That's an open question. So this is joint work with my student Zaiwei and Shang Kong, who's a grad student in ISYE, but not my student. And this result was published. It was presented in Sigmetrics last week. So my final conclusion, the one single message I want you to take home, even if you forget everything else. So if I bump into any of you 5 years later, I don't expect you to remember anything from my talk except this sentence. And the thing that I want you to take home is that if you're looking at stochastic process limits, heavy traffic limits of queues, steady state limiting behavior of SGD, whatever it is, you should always think about transform methods. Transform methods are powerful, and they make complex problems very simple. So I believe many of you are ECE students. I was an ECE student when I was a student, but now I'm in ISYE. As ECE students, you learn transforms, Fourier transforms, Laplace transforms in undergrad. But once you get into networking, essentially you forget all of them. So basically, I think the message is don't forget them. Transform methods are powerful. You can use them for networking problems as well. I went a little bit over time, but I'll stop here and I'm happy to answer any questions.
Thank you, Dr. Siva Theja. Yeah, we can take questions now.
So I have a couple of questions, but I'll wait. If others have questions, maybe they want to go first. But if none, then maybe I'll ask my questions. So maybe if you go back to your initial few slides.
Okay.
So first thing was that there was I think one thing which you sort of skipped, which maybe is trivial to prove, that expectation of U divided by the
correct. It's actually not trivial. That's a very good question. I kind of skipped it because of time. Where is that?
Yeah, this one, right? This expectation U squared 2 mu minus lambda. This is
right.
This is constant.
Correct.
So I would expect all the work is here, right? Or most the difficulty, because everything else.
No. Actually, this is not the work. In single server queue, this is pretty straightforward. I can tell you why this is like this. So mu minus lambda is like epsilon. So there's an epsilon sitting in the denominator. And I'm telling you this is constant. So you should be suspicious. But there is an expectation of U square, right? So what we do is we assume, I should have told you this, but we assume that the arrival distribution and service distribution has finite support. They say A max and S max that bounds arrival.
I see. Okay.
That can be relaxed. In single server queue, we know how to relax it. In other cases also, it can be relaxed, but it will just make it slightly more technical. The proofs will become technical. So suppose you assume the A max, S max thing, then this U square can be written as U times U. And U is unused service. It's upper bounded by potential service, which is bounded by S max. So you can pull out an S max. So this becomes S max times expectation of U. And expectation of U is epsilon. Why is expectation of U epsilon? Suppose you believe expectation of U is epsilon, then that epsilon cancels the denominator epsilon. This becomes S max over 2. And that's a constant, as I promised. And why is expectation of U epsilon? Take Q as the Lyapunov function, set its drift to 0, which means basically set expectation on both sides of this equation. And use the fact that in steady state, this guy is same as expectation of QK. So this cancels with this Q. Then expectation of Q is basically same as the expectation of S minus A, which is mu minus lambda, which is epsilon. But to say this without math, you have arrival rate lambda, service rate mu is greater than lambda. So the unused service should be mu minus lambda epsilon. That's why expectation of U should be epsilon in steady state.
No, but I didn't understand. So U square, you're saying, is less than equal to mu minus epsilon, right? For U, I understood.
No, U is epsilon. Expectation of U is equal to epsilon. Expectation of U square is less than S max times epsilon. S max is the maximum possible value of the
I see. Okay.
service.
Got it. Mm-hmm.
And S max is, so I'm making the equality into an inequality when I put the S max thing, but in the limit, this term goes to 0, so it doesn't matter.
Okay, thanks. So one more question. So maybe this next one is a little bit more about the, so can you go back one more slide?
Okay. Back.
Maybe the beginning. So the two methods you didn't want to, you didn't comment on. So I just wanted to get a sound bite out of you for the Stein's method and the other one which you skipped.
Okay, very good. I have a slide on drift method. I have a slide on diffusion limits. I can tell you a little bit about it. Stein's method, I don't have a slide, but I can tell you about that as well.
Right.
So actually, if we take a step back, everything is central limit theorem. So how do you prove central limit theorem? Like if I teach a class, the proof that I do is the one-page proof of using characteristic function, and then Taylor series, and then killing the terms and so on. Transform method is analogous to that. Before this characteristic function method of central limit theorem was proved, people looked at moment method. You look at the first moment of the limiting value, second moment, third moment, and so on, and show that those match Gaussian. Therefore, the answer is Gaussian in central limit theorem. So the drift method is analogous to that. The diffusion limit method also has central limit theorem, but central limit theorem on steroids. So essentially what people do is the following. So in drift method and transform method, we were working in steady state. But in diffusion limit, people work it with transient. Look at my Q length update equation. It looks something like this. Now look at the stochastic process. I was only working with random variables, which are the steady state distribution of the Q length. But now look at the entire stochastic process. Now scale the stochastic process appropriately. You have to scale time and you have to scale magnitude also. And then if you take the limit in the heavy traffic, and the scaling depends on epsilon, one of them is epsilon, the other guy should be epsilon square for reasons. In the limit, one can show that this is some kind of SDE, stochastic differential equation. For a single server queue, indeed, this is like a reflected Brownian motion. What's a reflected Brownian motion? It's a Brownian motion. It has negative drift because mu minus lambda is epsilon. So it has negative drift. Lambda minus mu is minus epsilon. So it has negative drift. It has some finite variance. The variance depends on the sigma square, the average of sigma squares. But Q length cannot go negative. So there's a barrier at origin. It just prevents people from going negative. So this is called a reflection. This corresponds to this bracket plus Skorohard map, all of that. And this reflection is very important. Now I can ask you, if I have a reflected Brownian motion. So now the idea is the entire time evolution of the Q length process can be approximated by this RBM, reflected Brownian motion process. And then I can ask you, what is the steady state distribution of this reflected Brownian motion process? If it's positive drift, it goes to infinity. If it's zero drift, it will kind of spread out and go to infinity. Because it's negative drift, it's going negative, but there's a barrier. So intuitively, it should have a steady state distribution. One can show this, in fact, done in one of our PhD level courses at ISYE. One can show that the limiting distribution of RBM is actually exponential with exactly this name. And then the next question is, so far it's, so this getting the RBM, it's like standard machinery that depends on functional central limit theorem and so on. And then once you get the RBM, studying it is straightforward. It's in standard Brownian motion textbooks. Then the next thing is, okay, fine. The steady state of this RBM is exponential. What you did is you took your Q length process, scaled it appropriately, got this RBM. This guy's limiting distribution is exponential. But what I am interested in is I take my Q length process, and then I let time go to infinity to get its steady state. And I'm interested in the limiting distribution of the steady state. So there is a limit interchange issue. Then the question is the limit interchange true? If the limit interchange is true, then that would imply that the steady state Q length converges to exponential. Indeed, in single server queue, one can show this. But once you look at more general systems, showing this limit interchange turns out to be extremely challenging. So many results actually skip the limit interchange step, and they either some papers only work with showing the limiting SDE, stochastic differential equation. Some papers work on studying the limiting stochastic differential equation, and some papers are written just to show the limit interchange issue. So this is the diffusion limit. So the way I like to say it is, if I have an incoming grad student and I want them to understand that the limiting heavy traffic limit of single server queue is exponential, if they want to understand it using diffusion limits, it'll take them about a year or a year and a half. because first they have to go do courses on measure theory, probability, stochastic processes, so that they're comfortable with functional central limit theorem, Brownian motion, and so on. Then they can actually read this paper and then understand this. On the other hand, if you work with drift or diffusion or transform method, you can get it in one slide. I mean, I had the entire proof in 2 slides right here. So that is the simplicity of transform or drift method compared to diffusion limit. But diffusion limits, if you forget about the technical details on diffusion limits, I think diffusion limits give very nice intuition. The intuition is that, oh, whenever you have a queuing system like this, you can, without doing any of the math, on scratch paper, I can write down the corresponding Brownian SDE that I should expect. And then I can do back of the envelope calculation to look at what answer I should get, and then use those to prove things using other simpler methods. So that's a diffusion limit approach. Then the Stein's method takes a slightly different view. Stein's method is used to bound distance between 2 random variables, which means one can use it to get rates of convergence. So I only told you that epsilon q converges to exponential. Then one can ask, if I give you a finite epsilon, finite small epsilon, 0.01, the distribution of epsilon q is not exponential. How far is it from exponential? Can this be characterized? So I didn't talk about it in the presentation, but drift method and transform techniques can be used to give some bounds on this error. But let's keep that aside. Stein's method is a different method to actually give this bound. And again, I'll not get into details, but it's again inspired by Stein's method for central limit theorem. So I can go back to central limit theorem and then ask, the limiting guy is Gaussian, but if I don't take the limit for large enough n in central limit theorem, what is the error with respect to Gaussian? And Stein's method was developed to actually bound this. Berry-Essien theorem was actually the theorem in 1920s or so, which characterized the rate of convergence of central limit theorem. But in 1960s, not 60s or 70s, Stein came up with a simpler method, a lot simpler than Berry-Essien, which actually characterizes the rate. And the Stein's method in queuing essentially was a very great generalization of the Stein's method for normal distribution. So does that make sense? I think the question was simple. I went on for 10 minutes. But
No, it was good. Thank you. I just wanted to hear from you. Thanks.
I had a kind of very general and basic question. So in all your analysis, you have considered infinite queues. Why not finite queues analysis? Or is it too trivial to do?
Oh, you mean truncate the queues?
Yeah.
Okay, so what happens if you truncate the queue? Then again one can ask, what is the distribution of queue length, right? It should be the answer should be between 0 and b. B is the buffer size, and it's not possible to get a closed form expression for this. And if you look at heavy traffic, if epsilon goes to 0, then the queue length is always going to be b. So it becomes trivial. So I shouldn't say that whole problem is trivial. In heavy traffic, it becomes trivial. Then you can ask, oh, why care about heavy traffic? Can I look at some other regime? So I don't know if there's any other regime when this finite buffer thing actually makes sense. There are some mean field results that assume finite buffer, but those are almost like technical conditions. They don't want to deal with certain hard technical issues, so they assume finite buffer, but the finiteness of the buffer is assumed to be large enough so it doesn't matter in the analysis. So I guess my more higher level answer would be that one purpose of heavy traffic analysis is to gain intuition. It's a limit theorem. It's like saying, what is the use of central limit theorem? If you have a lot of random variables and you average them without doing any calculations, you can approximate it by Gaussian. Similarly, if your traffic is fairly large, you can approximate it by exponential. So to get such kind of limit theorems, I think when you have, at least in heavy traffic, when you have finite buffer, I think it becomes trivial. Does that make sense?
Yeah, okay. Yeah. And I was going
to if you change the buffer with respect to epsilon, now I think it gets interesting. I don't think that is done in the literature. I think that's a very interesting future direction. So what you can say is, I'll take my buffer to be 10 over epsilon. My queue length is increasing as 1 over epsilon. I'll increase my buffer also. Then in the limit, what will you get? But what, so I think that is probably a non-trivial question. My guess would be that you should take this exponential and then truncate it. Maybe that will be the answer. Does that make sense?
Right. So you preempted my question. Like I was going to ask, what makes the heavy traffic regime most interesting for modelers? And like, because coming from a practitioner, you don't want to operate in heavy traffic regime.
That's true. I think this is like, I mean, you found the Achilles heel of all of heavy traffic theory. I think it's a beautiful theory, but in practice, like you said, you don't want to operate in heavy traffic. That's why I had the slide. I don't want to drive in heavy traffic. That's why I go late and I come back late to work. But I think my take on it is that we talked about switch, max weight, distribution. In the presentation, I focused on the distribution. I stated the mean result, but one can actually show that the mean Q length is very close to optimal. I showed the mean Q length formula under max weight in a switch. One can find a lower bound and one can show that it is very close to optimal, which means max weight is close to optimal in heavy traffic. Maybe that suggests that max weight is close to optimal in non-heavy traffic also. I mean, this is a big leap of faith, but if it turned out that max weight was not even optimal in heavy traffic, then there is no reason to expect it's not even optimal in heavy traffic. Let me put it differently. Are you familiar with load balancing?
Yeah.
Okay, good. So in load balancing, you have a bunch of queues. You want to send an incoming arrival to one of the queues. Three algorithms I can think of. Number one, random. I close my eyes, toss a coin, send the arrival to one of them. Number two, join the shortest queue. Number three, power of two. Power of two means I toss a coin, find two queues at random, compare their queue length, send to the shorter of them. Now, in heavy traffic, power of two and JSQ have exactly the same behavior, but random has order of magnitude worse behavior. So this shows that you should never be using random. Random is terrible. And maybe you can't do JSQ because you don't want to keep track of all the queue lengths and compare them and so on for every arrival. But even if you do slightly more than random, like power of two, you're already getting a lot of benefit. This is a message that you can learn from heavy traffic, which actually is true in practice also.
Thank you.
If there are no more questions, let's end this session. Once again, let's thank Dr. Siva Theja for an interesting talk. As discussed before, we would like to remind the audience to subscribe to our Google Groups, which is the mailing list for information on future talks. You can also visit our website for more details. The links have already been pasted in the chat box. The link to the recorded video will also be pasted on the webpage. Thank you and have a great evening.